second session. It's my honor to introduce our esteemed resource person, Dr. T. Chandrasekhar sir, who has been our resource person for the first session on the beginning of this FDP, a distinguished academician and researcher in civil engineering. He currently serves as the professor and head of the Department of Civil Engineering at Bapatla Engineering College, Autonomous. With an impressive 34 years of teaching experience and 24 years of research, Dr. Rao has made a significant contribution to structural engineering, specialization in ferro cement, fiber reinforced concrete, ultra-high cement concrete, and geopolymer concrete. He has authored over 126 research publications, many indexed in Scopus and Web of Science, and holds multiple patents in advanced concrete technologies. Beyond academia, he was served as Board of Studies member, technical advisor, and PhD supervisor, mentoring the next generation of engineers. He is also an award-winning researcher, recognized internationally for his contribution to civil engineering. We are privileged to have him us today. Please join me in welcoming Dr. T. Chandrasekharao, sir. Over to you, sir. Very good evening, sir. Over to you.
Is audible? My voice is audible?
Yes, sir. Your voice is audible, sir. Loud and clear.
Once again, I myself, Dr. Chandrasekharao, presently working in Bapatla Engineering College as the head of the department. So, on the inception day, I have met all these resource persons, but on that day, due to some technical issues, I am unable to excel myself. The complete what I have to transform on this CNN model in the civil engineering applications. But finally, on that day, it was gone out. But today, as a part two, today we'll see the crack detection using ANN techniques. That is the primary one in concrete structures. So these slides are clear enough to everyone. Yes. Hello? Hello?
Yes, sir. You're audible, sir.
Oh yes. Okay. Then I will go. So this is the main theme of our presentation. Concrete strength, that part is strength evaluation is completed on the first day itself. And this as a part two, today I want to crack detection. Crack detection, how will you crack detection will be made by you this. So there are so many ways. First of all, we'll see what is crack. Crack is nothing but a split or a break in the concrete. When will it occur? When the stress induced in that concrete is greater than or dominates the stress induced is greater than the strength of that concrete. Automatically, the crack will induce in that concrete. So the cracks, even before in fresh state, in green state itself, the crack may occur. So the cracks are generally termed as the shrinkage cracks. So whenever the loads in hard state, whenever finally the structure is intended for to carry the loads, so when the loads are applied, automatically the stresses induced are greater than the strength of that existing member. Again, the cracks will appear. So finally, the cracks are inevitable in the concrete. We cannot avoid that. Finally, what we understood. So how to travel with the cracks? Crack-free concrete is everybody is from the last so many decades. Every researcher is searching for to made crack-free concrete, but either in any other state, either in fresh state or in hardened state, the cracks are appearing. due to so many reasons. Even if you maintain a good quality of concrete, even if you select a good quality of materials or workmanship or machine applications, whatever the case, finally the cracks are inevitable in the part of a body of a concrete. So, how to detect these cracks is generally in normal state. We will generally will say, we will identify the cracks by naked eye, by vision. Or if the cracks are severe cracks, we can say these are severe cracks. The intensity of crack you can measure by using some measurements, scale or something, any equipment. You will take that. Last session we have discussed about that. So that is the normal one. Suppose if you take a high-rise structures or bridges, the cracks are appeared or developed. So the detection and intensity of and knowing the intensity of crack itself is in a normal board is a very uh, tough one to an engineer. If we task for an engineer to evaluate these cracks, whether they are dangerous or is it normal cracks. So in that case, nowadays, so the technology has emerged like anything in the present scenario. So being our civil engineers, we will adopt some of the techniques which are in the recent developed in computer science engineering. One of the technique is artificial intelligence. In artificial intelligence, ANN is a major one. Artificial neural networks. Neural networks is nothing but it imitates our brain, human brain. So that in that model, they have developed a lot of models and a lot of branches in that. So I have taken that as a reference. That one of major kind is the machine learning or deep learning. Both are same. Working on the way the behaving. Last time we also discussed. Again, we are refreshing. So finally, coming to the point, the for crack detection, here we will see image processing by using computer vision techniques. Crack detection in the concrete by using image processing. So this is what we have already discussed. Coming to the crack detection is crucial for maintaining the structural integrity. Analyzing the images helps the identifying and assessing the cracks. So for a how to get the cracks images, one of the major kind of that one is. One is real time gathering, collection of the images. That means you go with a camera or you send a drone. It will, wherever the structure is gets cracked, it will pick up all the images and you gather that, you get the data from that a drone or your high resolution camera. You download that in your system and then you analyze what type of cracks and how intensely whether they are mild cracks or severe cracks. You can separate it out. Suppose for example, a lot of data is in our websites. One of them is major one is Kaggle. So that data is uploaded by someone. Anyone can browse that. For a today demonstration, I have downloaded that one, Kaggle. So here, there in Kaggle, the data set for crack image, data set for cracks in concrete. So there I got 40,000 images. 40,000 images, just you imagine. In that, 20,000 images are uh, no cracks, and 20,000 images are cracked images. Finally, 40,000. So by using this data set, uh, just a minute. uh, so is my screen is fully covered?
Yes, sir.
Some of
Fully covered.
so
Slides
my
are not
scholar
covered.
has sent a message for me. So is it covering all?
Yes, sir. The slides are covering all.
Okay, okay. If everything is okay, then it's okay. So the data set I have used for this image processing process, how the crack detection will be carried by using all these images. 40,000 images is a very huge data. You cannot use it. The model cannot run. It will upset. So then I will gather all the whatever the major more clarity and more intensify cracks are there in images. That data set I have collected. So for that I have taken nearly to 3,000 roughly. Actually, I didn't done one. That model is running out today. Nearly 40,000 images for cracked images and nearly to 1,500 uncracked images. That data set I have collected for the testing the crack detection using image processing. You understood like that. So in that, the first step, how to carry the image processing by for a crack detection is data collection. Gather the diverse concrete images and immediately you go for the pre-processing. Pre-processing, what is pre-processing? That means convert images into grayscale to reduce the noises. So the first one is what I said is pre-processing. Pre-processing. Pre-processing means is the process of converting raw data so that it can be used for machine learning algorithms. So what are
Pardon,
the
sir.
data?
Excuse
Hello?
me, sir.
Uh,
The slides aren't moving, sir.
they are not moving?
Yes, sir. The slides aren't moving.
Okay.
We are still in
That I
our
will check.
screen, sir.
So still it is showing your first slide.
Yes, sir.
Okay, there may be some problem. Okay, I'll find out. I will close. చూడు ఒకసారి ఒకసారి అడుగు హలో
Yes, sir.
హలో
Sir. Mhm. Mhm.
Okay. Now it is okay.
Yes, sir.
Ah,
Kindly move any
just
one
you see
side, sir.
whether my slides are moving or not.
Yes. Um, Page is loading.
Okay.
Yes, sir. The slides are moving, sir.
Right, right.
Thank you, sir. Thank you so much, sir.
Every time you are getting some issues. Okay,
Yes,
right.
yes.
So this type of issues are very much well versed when I am teaching on online Corona time. So this time, okay, right. So finally, this part is over. So finally, what I want to say is crack detection by using image processing. Okay, for that I have used some data set from the Kaggle. Okay, in Kaggle there are 40 that 20,000 images are uncracked images and 20,000 images are cracked images. That's it. Okay, then by using this still by using this data set, how to carry the workflow for crack detection in image processing. The main the concept is image processing. So what is image processing? So image processing means you are processing the image in the different stages. So with the raw data to the finally tuned data, so that you can detect you can get all the details by with the naked eye. You cannot see whether the crack is how much width and the length and the intensity. All these data you cannot by you get by using naked eye. So by using this CN image processing techniques, you get all this data. That is the main advantage of this one. And a lot of data you can be analyzed at a one stage by you creating a model. So the first step is gathering diverse concrete images that may be any website or you can get in real time. And then the second one is pre-processing. And third one is crack detection, feature attraction, and classification. We will discuss one by one. The step one, what is pre-processing? What is pre-processing? Pre-processing is the process of preparing raw data so that it can be used for machine learning algorithms. That is the pre-processing. And at the same time, it will reduce the noises. It will also reduce the noises using filters to enhance the crack detection and helps the better feature attraction for classification. And the second one is how will you crack detection techniques will be adapted. That one is the edge detection by using canny edge detectors, highlight the crack boundaries. And next one is thresholding. Thresholding means separate the cracks from the background. And these techniques enhance visibility of cracks in the images. And the third one is the feature attraction. Feature and then classification. So crack features such as length, width, and orientation. This is the final output we finally you will get. Finally, by using this image processing technique, if the machine learning tools also you will combine with association of this image processing, you will get more and more data. That one is CNN. CNN is convolutional neural network, and YOLO. YOLO means you only look at once. All these one models will associate with this one. Example, again I have taken. So this is how the model will run. In the first stage, here you see, go back. You see, in step one, it's an input where the image is grabbed from the camera. So import the image from the data source. And this is in a colored image, RGB. Somebody is calling. Hello? And the second one is this one, RGB. That is in a color image. This will be converted into a grayscale image. That means to reduce the noises. A color image, it will have some pixels of the image sizes of that means the 1000 by 1500. So such image you cannot analyze. It will a lot of the model has to be run more and more. It will get strained the model. Then it will be converted into grayscale. Grayscale means like this. The color image will be converted to grayscale. In that, the image will be converted in the gray mode. In this, it will be only two. One is in white and another one is black. So that means it will be converted into a normalization scale 1 0 to 1. Then generally the pixel values are from 1000 by, suppose the image size is 1000 by 1500. That is 1000 is the width and 500 is the height of that pixel value, that image size. So this is the second one. RGB will be converted. RGB means red, green, blue color processing to grayscale to reduce the noises and contrast enhancement. This is the second step. This is here. It will be, you see, the color images will be get converted into a grayscale. And third one is the crack extracted the images and the edge detections. Suppose here it is a crack. This crack will be here. It will edge detection. It will be identified by using these edges, where the edges are there, how this crack is propagated, is there any curve mode or straight line mode, like this, all this one. Here the segmentation will be, that means it will be divided into number of pixels. And the third one, finally, feature attraction. Feature attraction means finally our output, what you are aiming for is crack. What type of crack is, the intensity of crack is, how much width it is, how much length it is, what type of crack it is, whether it is a flexural crack or a shear crack or any combination of these two, or longitudinal crack, like this. There are so many types of cracks are there in a beam or a column or a slab. Generally, this type of cracks will be your cracks in these structural elements only. Suppose I have taken one image from the Kaggle, already this one. First one, this is the beam testing. In this, a crack was found. This is a color image. This color image crack is converted into grayscale. In grayscale, it is black and white, it is converted into. So black represents the uncracked portion and white portion represents the cracked portion, where the crack is intensified, and the edge detections are made in the next stages, and finally it will be converted into output format. So image processing. So grayscale conversion simplifies the image by reducing the shades by gray, and at the same time noise will be reduced. So this part is already I explained. So generally we will use this image processing software technology for using OpenCV. So image filtering, edge detection, morphological operations, and the thresholding. Otherwise, you can use this software. So what type of software? Generally, the audience may get doubt. Sir, what type of software you have to be used? Generally, in civil engineering, we know a STAD lab, AutoCAD lab, otherwise any softwares. So many softwares are there for geotechnical. Like that, you how to run this one. So these softwares are very much used. You have to download from the one OpenAI, manaki, OpenCV, MATLAB, image, and Photoshop or GIMP, and Scikit images. So these are the different softwares available in the Google. You can directly download. Some of majority of that free downloads. And this one is a category. For pre-processing and image analysis, we will use OpenCV, computer vision. CV means computer vision, Scikit image, and MATLAB. And these softwares are very much useful for deep learning models, CNN, and machine learning models. Suppose if you use machine learning model for crack detection, use this one. Suppose you want to use deep learning models, use this one. Best option. So it is only in a suggestions. For simulation softwares, anyhow, these are we are using in our research works, ANSYS, Abacus, and Cosmon. And the cloud-based tools, Google Colab and iOS and Azure. So Google Colab and Azure are very familiar for everyone. So the session is not at over. Today I want to go in brief about this image processing technique. But one of my scholar T. Sivasai Hoshta, she is pursuing her PhD in Sapienza University, Rome, Italy. She is very much working on this area. So this image processing, I am not gone very much in detail because a lot of work was carried out on this. Because if I gone for a literature survey, so many works are I am found. You can find this one. So there are different techniques. Everybody is using computer persons, computer engineers. They are very much using as an application. One of the application, civil engineering application they are using. So what kind you can go for a better? Is it image processing or better, or DL model is a better, or ML model is a better? There are so many categories. Which model is better for crack detection, and which one is more accurate? Compared to image processing, DL model is seems to be better one. That what I understood from the that research works, the previous research works. So the one of my scholar, T. Sivasai Hoshta, she is she her research work on the same content by using wave mix theory. It seems to be a good one compared to other established ones. Now she will continue with her opinion and with her founding findings in today with us. Now I will introduce with the permission of the resource person, other resource persons and management and principal of the Space Engineering College and the head of the department, Ganesh Naidu. Shall I join?
Yes,
Ganesh
sir. Yes,
Naidu?
sir. Yes, sir. With all pleasure, sir.
Right. So, Sivasai Hoshita, are you Sivasai Hoshita?
Yes, Ms. Pushta, you're unmuted now.
Uh,
Yes.
can you hear me?
Sivasai. Okay.
Yes, Ms. Pushta, loud and clear.
Okay, thank you.
So, a brief introduction about Sivasai Hoshita. She did her BTech from in India and Andhra Pradesh, Machilipatnam. Later, she went to pursue her MS from Rome, Safin University, one of the prestigious university, ranked below 200 in worldwide. And at the same time, she is continued her PhD there itself. She is also carrying in the same our civil engineering field, particularly railways. Now, it's a time to Sivasai Hoshta, share your one of your findings with us. So I am
Okay.
stopping my sharing.
On behalf
Yeah.
of BEC Institute of Technology and Sciences Civil Department, we welcome you, Ms. Shivsai Pushta. Thank you for being here.
Thank you. Thank you, sir. Thank you for your invitation.
I am not comfortable. అదేదో తీసి నేను ఏం చెప్పలేకపోయా రీసైజ్ చేయాలి నాయిస్
స్క్రీన్ లేదు మెసేజ్ పోస్తా డిస్టర్బ్ అయిపోయింది
అది
Can anyone see my screen?
Yes, and we can see your screen. Kindly share the PPT.
Okay, now is it clear?
Yes, the presentation is clear.
Okay.
Excuse me, ma'am, can you go for the full screen mode? And
Yeah, okay.
just move 1 or 2 slides. It's for the casual check yes, ma'am.
Is it okay?
The slides are moving. Yes, ma'am. Everything is clear.
Okay.
Perfect.
Okay.
You can
Thank
move
you.
on.
Thank you so much.
Thank you.
So good evening, everyone. I am T. Sivasai Hoshita. is pursuing my PhD in Sapienza University. I am my focus is on crack detection in the railway components. So I'm pursuing in Sapienza University. I'm very much thankful to my guide, Professor Vichi, and my co-guide T. Chandrasekharao sir, and and also the session. I'm very much grateful to having me here. So today I would like to discuss briefly about the crack detection in the concrete elements or components using the wave mix model. So this is what are the automation and the technologies we are using here is the technologies we use here is the sensors and artificial intelligence, robotics, and data analytics. We use the automation techniques here because only to improve the efficiency and also for the accuracy and the reliability in the construction and the material testing process. So why we use the automation here, what it does. Basically, like the robotic systems, they perform strength tests on concrete, and they also instantly record and analyze the test data. And it is also important because it eliminates the manual errors and provides faster and more accurate results. By using these artificial intelligence analytics, like the machine learning models and the deep learning models, we can also analyze the concrete mix properties, and it also predicts the future strength and durability. It also helps to optimize the materials what we are using in the constructions, and we can also improve the long-term performance assessment. So the automation basically allows us to do the things very quickly than we do manually in our day-to-day life. Um, Okay, so in this case, the automation in the strength evaluation, if we use AI and IoT, Internet of Things, robotics, and the sensor technologies, in case of the real-time data collections and analysis, the automation is very much we can like for example, if we want to um, uh, optimize a mix design, so we can generally we do some use codes and we do the manual calculations. If we train a model, we can also do like trial and errors instantly with automation. And for the AI based predictive analysis, uh, can you hear me?
Yes, ma'am.
Okay, thank you, I'm sorry. Okay, so for the AI-based predictive analysis, machine learning models, here we can analyze the concrete mix properties and to predict the future strength and durabilities. And in case of the real-time sensors monitoring, we can also monitor the structures and the components of the concrete components. We can use like sensors and we can monitor those components in real time, like the smart concrete embedded. There are some embedded sensors with the IoT installed. They monitor the strength variation, like during curing or later assessment after completion of the construction of a building or any component. And this is the general causes of the crack, like mechanical, physical, and chemical, environmental causes. Okay, now here the automation tools in the concrete strength evaluation. Here we can see the machine learning and AI based system. Generally we use deep learning algorithms and neural networks. And also these are the non-destructive devices. They're in common use today in the strength evaluation. Um, and the recently they're using the robotics and drones, the autonomous drones and the robotic arms, and there are some IoT embedded smart concrete tools like wireless embedded sensors and cloud-based data storages. Okay. Now, how we use machine learning and AI-based systems for the strength evaluation. So here, like the machine and deep learning for the structural health monitoring, deep learning models for the concrete detection, like fine tuning or pre-trained like CNN architectures, like we use VGG. These are the CNN architectures: VGG 19, ResNet 50, Inception V3, and EfficientNet V2. These are all the architectures used in the CNN models. And there are also many GoogleNet or ImageNet. These are YOLO. These are all the advanced deep convolutional neural network models, which are used for identifying the cracks as well, for like object detection and image classification, for detecting the surface cracks in the concrete structures. And the secondly, we see the cross swim transformer skips. This is the new approach model. Generally, it is a transformer-based model for crack detection. Like it uses the skip connections. These are all the models generally use, like which is it is transformer-based or the architecture-based. It is completely dependent. Today we are talking about, generally my topic is on the wave mix. It is completely the wavelet-based, like the waves. The model is completely trained on the wavelet based. Okay, so for the image segmentation, the concrete cracks, here it is using the convolutional neural network for the image segmentation. There are some researchers designed an end-to-end segmentation model based deep residual network. It improves the detection accuracy by effectively capturing the crack features. And also there is autonomous scan machine using an UAV, which it is an unmanned aerial vehicle with an onboard camera. There is a camera installed on the vehicle. So this approach generally aims to identify the crack detection and assessment efficiency in the concrete structures. And also the drones are equipped with the high resolution cameras to capture the images from the bridge components, because the bridge is a huge and heavy structure. So the drones are used to identify if there is any cracks or is any damages on the heavy or skyscrapers, on the heavy buildings. So these are all the images and the data set are captured and stored in the cloud-based storage. Okay, here we see the three images. Here we see the first image. These three are the robots. The first image we see here, it is SP1200. It is the concrete pumping and pouring. It automatically pumps the concrete. And the second one is it is intelligent steering mobile concrete pumping. It is also concrete pumping, but it is self-steering device. It self-steers and pumps the concrete how much quantity you want at the particular site. It automatically we can store into the device, and it pumps the concrete into the site. And the third one is the crawler concrete pumping. These three are the automatic pumping devices, concrete pumping devices, machines used in the construction site. Okay, here we see the deep learning. Actually, we can see the deep learning as previously Sir told you about the deep learning. We can see the deep learning has different categories. We talk about the CNN, convolutional neural networks, vector neural networks, and feed-forward neural networks, LSTM, and GANs. So, but generally in every deep learning models, like for if you want to analyze image, or if you want to detect an object, a particular object, if you want, for example, for the image classification, if you take the images with the cracks, if you want to classify and separate the images, Like if you have the data set with 40,000 images, the 40,000 images have some data set with the cracks and the other data set without cracks. If you want to analyze the images with the cracks and no cracks, we use generally we use convolutional neural networks. And the convolutional neural networks, there are different models here. Here I have mentioned LENet, AlexNet, VGNet, as I said before. These are all the models we use for the image classification and object detection. Each model has its special category. Like if you want to use the AlexNet, it is completely depend upon the how many convolutional layers is the model applying. For example, if the AlexNet has the 3 convolutional layers, the VGGNet goes to the 5 convolutional layers. Like it is completely depending on the how many convolutional layers the model has trained through. So, for the deep convolutional neural network, the object detection, we use the YOLO. You look only once, and the ResNet. And there are also other models that I haven't mentioned here, like faster RCNN. So our faster RCNN and YOLO are the very much used nowadays for image classification and object detection. So for the crack identification, so let's come, for example, I have made a small program, like I have took some image data set with the cracks. So the each crack image, like the data set has, like, for example, I have 100 crack images. We have stored the crack image data into the model. If you want to store the image data set into the model, we have to write a prompt that if you use the Google Colab, we can mount the Google Colab with the Google Drive. So it directly goes to the Google Drive and search for the file or the folder with the crack images, and it takes the folder, the file with the crack images into the model. So at first here we take the crack images and we annotate the crack with bounding boxes. Okay, so if, for example, if we are asking the model, I want the images with the cracks, because the model doesn't know what are the cracks you want. So at first we have to train the model with the crack images. Like if you, for example, you split the images into 2 folders, the train data set and test data set. In the train data set, you put the images with the cracks, and you can also draw the bounding boxes, like the green color boxes, using the label image or RoboFlow or CVAT. You can use these 3 tools to create a bounding boxes, like to annotate the cracks. You can use these 3 tools and the create a data set with the cracks. So the model learns the type of cracks. Okay, this image has the crack. This crack looks like this. This is the flexural crack, or this is the shear crack, or this is the longitudinal crack. So the model trains according to the data or the images, how you train the model. So it learns the cracks. So after that, you save the data and you enter the saved data into the model. So it trains the model, and then it learns, okay, these are the cracks, and it tests on the other data set, unseen data set. If you give the laboratory test data set or the field data set, you give just the test data set. It already learned in the train data set, so it gives the very good accuracy and gives, okay, these are all the data set you have provided me. These are all the cracks from your test data set. So how the model learns, how properly the model learns, that much accuracy it shows on the test data set. So here we have I have used YOLO v5 and I took the real-time crack detection. So from the above, I have annotated from the annotated crack data set. I trained the model, and the model learned to detect the cracks. And finally, the run detection on the test images, the crack images with the I will show you. This is the test data set I have given. These are all the some images. I have took the sample images. I just wanted to show you. These are all the sample images. The first I took some images. I used the RoboFlow tool and created the bounding boxes around the crack, and I gave it to the model, YOLO model. So the YOLO model learned from those crack images, and then I gave these images, not only 5, and there are more, but I have put here only sample images. I gave these images, so it successfully detected the cracks and gave the bounding boxes. So you can see on the test data set, it identified the cracks. Then for this is for the crack detection, we can also call how we are converting into the grayscale. So the pre-processed version of the concrete crack images are likely enhanced for better feature extraction in deep learning models. So these are the images I have used. You can see the black and white high contrast effect. It shows that these images have undergone image processing techniques such as grayscale. To convert to the grayscale, the crack detection is completely depends on the contrast. By converting these images to grayscale, this grayscale removes the color. Here you can see the function CV to CV color image and the color BGR to gray. This function used to convert the color image to the grayscale image. And for the edge detection, I have used the canny edge detection, and there is also other one is a Sobel, but canny edge detection is a very much well-known function. This function we can use to detect the crack boundaries. Like if you take the image, this is the boundary of the this is the boundary of the crack. These are all the edges of the crack. So it identifies the edge of the crack. So for this detection of the crack edge detection, we have used the CV2 canny function, which identifies the edges in the image. And finally, here I have used the adaptive thresholding. The adaptive thresholding, it normalizes the crack by converting the image to black and white. Here we have converted the image to black and white image and to clearly see the crack. Okay, now finally entering into the model, I have used a wave mix model. It improves the accuracy and efficiency. Okay, I will talk about my data set. Here I have took the data set with the cracks and the no cracks. There are the two folders. This folder contains no crack images, and this folder contains the crack images. So here we can say there are the two classes. One is the cracks and no cracks. Then the libraries I have used is PyTorch and the WaveMix. And this is the WaveMix is a model like we use the convolutional neural network model or YOL or feed forward network, and whatever model we use, whatever artificial model we use, WaveMix is a type of model which is not very much recently, but it is developed like one year back. But it is very much used nowadays for the image classification or for the object detection. It is showing the better results than the CNN models. So I have chosen this wave mix model on my data set. The cracks are normalized into the size 256 by 256, and also we can normalize to 128 by 128. And here the data augmentation, how we augment this data set, these cracks and non-crack data set. At first, to improve the image quality, like removing the noise and the contrast adjustment. As the wave mix works on the frequency components, it enhances contrast and removing the noise, which improves the crack feature extractions. To improve the crack features and removing the noise, if there is any blurred images, the image quality itself improves. It itself improves the quality of the image. So for that we have to adjust the contrast and remove the noise. And and for the crack size and the location, the cracks can appear in different sizes and different angles. The crack can be in any mode. There may be different sizes or different intensities. So in that case, we can use the rotations, like up to we can use from 0 degree to 360 degrees. So by using this rotation, it adjusts the image or the crack into the particular location or the angle. It adjusts a particular angle. If there is an image into the one side, it is into the it is a diagonal image or the horizontal image or the vertical image. It doesn't see here. We are not asking it whether it is a vertical or a horizontal or the diagonal image. We are just asking whether this image has the crack, this concrete image has the crack or not. So it it normalizes the angle of the image, and we can also adjust the angle of the image from 0 degree to 360 degrees. We can give any angle. Generally, most of them use 30 degrees or 45 degrees. This is the general use of the image rotation. And we can also zoom in and zoom out of the image to adjust the same size of the image. And also we for the class imbalance, for example, if the data set if there are more cracks images, if here I have shown you the no, if the crack images are only the 97 images or the 10,000 or 99,000 or images, no crack images are like 40,000 images. So there is the imbalance between the folder data set. So the crack images are less and no crack images are more. So for that we have to imbalance the data set. For this we can create the duplicate crack images. It's like oversampling images. So we can create we can give the function to create the duplicate crack images, and to create a synthetic data generation. We can use here augmix or GANs to create the synthetic data, the duplicate image data set. So it balances. If there is 20,000 images in the no crack, if there is 10,000 images in cracks, it creates another 10,000 image duplicate images into the cracks, and it balances 20,000 and 20,000. So it balances the data set. And finally, for the validation and evaluation, the augmentation, it does not cause any overfitting because of the class imbalance we have done previously. And for the train and validation split, here we have used 60% and 40%. Just a second. Okay, I haven't mentioned here, I think. For the train and validation split, for the training split, I have used 60%, and for the validation split, I have used the 40% of the data set. So from these overall images, 60% of the images it takes for the training, and the 40% of the images it takes for the validation. Similarly, we can use 70% and 30% and 80% and 20%. But the 60% and the 40%, it's the better choice. Okay, here I'm talking about the wave mix model architecture. Okay, here wave mix, it's generally uses the it's the wavelet transformers. It is the wavelet based neural network architecture to process images and other type of structured data efficiently. Structured data means it is a proper data set, proper crack image data set. And it also focuses on reducing the complexity of the model. Complexity means it is nothing but it is a particular algorithm consumes, like number of trials, like epochs. Epochs means how many image data set it is taking to train for the one batch. So that is the complexity. So it reduces this complexity. And here we can see this model consists of level 1 wave block and discrete wavelet transforms. It rearrangement the layers for the transformation. This is the general architecture of the wave mix theory. Here you can see the 4 main parts. For this image, you can see, because we have done here the image classification, I'm talking about this image classification line. Here you can see the input image. We have given the input image. It went to the convolutional layer, and then multiple wave mix blocks, and then MLP head and the global average pooling, and these are the different. I will explain you in here, and these are the different steps it is gone through, and we will get the out class. So how this process is from the input image to the output image, how the image is going through this model, we can see here. We can see it here. At first, the input image, here you can see H, W, and C. H is the height, W is the width, and C is the channels. Channels means the image, how many channels, like 1, 2, 3. 1, 2, 3. How many channels the image is divided. So for example, of the image is 128 and the width of the image is, I can show it here. If the height of the image is 128 and the width of the image is 128, the first input image is divided into the 3 channels. And then it is processed with a convolutional layer to extract the initial features of the image. It look into the image for the initial features in this convolutional layer, and then it this convolutional layer helps reducing the number of channels. It reduce. I have told you the channels is divided into the 3. It reduces to the 4. You can see here the 3 channels is multiplied into the 4, and similarly For every discrete wavelet transform, the channels are increased, the height of the image is decreased, and the width of the image is also decreased to the half. So you can see the image is zoomed out. It's zoomed out. Like 128 image is reduced to 64, and it is reduced to 32, and it's reduced to 16. 16 is it is looking a very deep into the image. It is looking and extracting the features of the image deeply. So you can see here level 1, level 2, and level 3. Okay, and so you can see here for the first level, the feature map undergoes into the 3 levels of the 2D wavelet decomposition, level 1 and level 2, level 3. And then at each level, this input is decomposed into the 4 bands. Here you can see the 4 bands. This is AA, AD, DA, and DD. You can see here AA means approximation coefficients, DD means detail coefficients. Approximation coefficients is nothing but it retains the low frequency features. The frequency of the image, it's the how much frequency is the low, it retains it keeps the same. And the detailed features, it means it captures the edges and textures of the image. So at each level, the same process is continued, and then the image is sent uh, to the to concatenate the image. Here the decomposed image, like after detecting the features and edges in the image, and it goes to the concatenate stage. Here you can see it independently processes the image after separating the edges and the features of the image. It deeply sees into the image, like where it started and where does it end, and is there any cracks or fine cracks which human eye can't see. It it zooms out into the image and see detailedly into the cracks. So is there only one crack, or is there any other crack that human eye can't see? So that happens here. Then here it means multi and the bad normalization here is what here the processed image is going through the different levels, and it comes to the concatenate, and here batch normalization means all the adjustments have been done. It's back to the normal, and we will get the output of the image. So this is the architecture flowchart of the model. Here we can see that 2D discrete wavelet transform means here the image process. It is an image processing technique. It uses the multi-scale analysis, and it gives the both spatial and frequency information. Generally, it is used for the feature extraction, deep learning, and image compression. Here in this model, we have included the wave mix based CNN model. For this, we at first we have to install wavelet wavemix. As I previously I have told you, wavemix have wavelet transforms. Here we have to install the wavelets and other necessary libraries, and here we have applied the hair wavelet. It is nothing but it is as I previously mentioned, it is a 2D discrete wavelet transform. For this, we have used the Haar wavelet, and to split the each channel. This wavelet is used to, like I have previously told you, like this. It converts into this grayscale images. So for that, this Haar wavelet function is used, and and then to reconstruct the original image, and then the wave mix based CNN model is applied. After that, we have to, after installing and mentioning these functions, the data set is loaded from the path we have stored in the Google Drive or in our system. We have to load the data set from the source, and then it applies the transformation and resizes into the pixels, into the 128 by 128 pixels. After the resize and normalization and converting into the grayscale images, we use we train the wave mix model using 10 epochs. We keep the epochs to 10. Okay. After that, we get here. You can see here LL, LH, HL, and HH. This is it is nothing but the wave mix based models. It generally shows how detail. You can see here. You can see here LH means horizontal detail. You can see here the detailed crack, horizontal crack, detailed crack. And HL means vertical detail. You can see the vertical line is highlighted more than the horizontal crack. Here you can see the diagonal detail. So this normal image is splitted into the three: horizontal, vertical, and diagonal details. Is my screen sharing?
No, ma'am.
Start visible. I think it
Not
was
yet.
stopped due to lack of connection. Just you check once.
Is it okay now? Is it okay now?
Okay. Share your way. Okay. Now it is okay.
Okay. Okay. Okay. I will explain again. So when I take this image, for example, I'm just taking an example of an image. If I load this image into this wave mix theory, into the wave mix model, it first shows the approximation of the overall image where the crack is there. It shows just the approximation of the image, and then it shows the horizontal detail of horizontal crack detail. Here you can see the crack is diagonal, vertical, and the horizontal. So here LH means it shows the horizontal detail crack, HL means vertical detail crack, HH means diagonal detail crack. So it splits the crack into the three different fronts. Okay. Yeah, here I have written that for the horizontal detail, the highlighted crack oriented horizontally, and the detecting crack runs vertically. And here it is the thin. Compared to the horizontal and vertical, diagonal crack is very thin. Okay. For this, okay. In this wave mix, in this wave mix model, for every model, not only wave mix model, for every deep learning model or the machine learning model, we have to use the optimizer. As an optimizer, I have used the Adam. Adam is an optimizer. It is an optimizer with dual opt. Okay, for this wave mix based detection, I have used this one. Here's the overall the breakdown of this optimizer, how this model has taken into its how it considered. We can say that if there is a lot of images with the cracks, for example, if there is a construction site with construction site of the buildings or the bridge, or the, whatever the situation, we take the different crack images. So maybe some of the images are the huge. Some of the images of the cracks are very huge, and some of the images are having a very thin cracks. So here we can say there is a varying intensities. The crack images have the varying intensities, the texture, and the backgrounds. So each image doesn't have the same background or the same intensity of the crack. It has different. Maybe the cracks appear under different lightning conditions. Maybe if there is an image with a very thin crack which is not visible, maybe we took the image in the shadow, it is blur, or maybe the camera is shaken. So for this situation, we have to create a robust feature extraction. So for this, the optimizers are used for the robust features extraction. For example, also in the case of the small data set, not only the intensity of the cracks, if we have small data set, there is a limited crack images. So we require the efficient learning techniques to generalize well this data set or the crack images. These optimizers also use. And in the other case also, very tiny cracks may be hard to see or to detect. We require the high intensity in the feature extractions. So because the model has to see a very tiny detail of the image, whether the crack is there or not, the optimizer is used here as well. And coming to this optimizer, it shows the training process of the wave mix with the Adam and dual opt. Initially, the model loads the wave mix for the crack detection and define the Adam optimizer with dual opt, which starts with a global learning rate. The learning rate is the very minimum. It is not more. It is point not one learning rate, which is a very low learning rate. Means the number is low, but the learning rate itself is the better number. And then to start with this global learning rate, this dual opt adjusts the learning rates per layer wise. It takes the layer wise. The image is converted into the layers, so it takes the layer wise and it optimizes. And then for the forward pass, the model process a batch of crack images. For example, we can tell the model, if we have like 100 images, we can tell the model to take batch wise, like you can take the 32 images at a time and learn in the one epoch. In one epoch you can take a 32 batch of images, like that. And then to compute the cross entropy loss, it generally measures the difference between the truth, maybe the actual labels and predicted labels. Means maybe if we give the number of images into the model, if there is no crack also, it is as a crack. Maybe if there is a clear image of the concrete, just a slab, there is no crack in that image, but the model itself takes it as a crack image. It itself gets confused and take that image as a cracked image. Similarly, if there is a crack image, it takes as a no crack image. So there is a difference. The model confuses sometimes. So that from that we get the accuracy, how accurately the model is trained. So these are all the model, whether it how many images it identified as the cracks and how many images it identified as the non-cracks. There are the true positive, true negative, true um, sorry. There are the true positive and true negative, false positive and false negative. Means true positive and true negative means yes, these are the cracks and these are the no cracks. False positive and false negative. Okay, these are the cracks, but I took it as a no crack. And these are the no cracks, but I took it as a cracked images. So there is a false. The model is thinking that the model itself get confused. So this the cause entropy law states that. And for this backward pass and the gradient update, this Adam optimizer updates the weights using some adaptive thresholding and the learning rate techniques. And finally, for the validation, each we took the 10 epochs as I previously stated. After each epoch, the validation loss is checked. The validation loss is checked. If the loss improves, the training continues. If the loss is not improved, the dual opt slowly updates to avoid overfitting. And the next one here, this is the model training process. Here, as I previously told you, I took the 6% of the data set as the training and the 40% as the validation data set. And for this, I have used PyTorch data loader. And this is you can see the cross entropy loss. This is the general formula. On my model, I got 0.2438 cross entropy loss. Means the model performed well and it is highly accurate. And these are the evaluation results. This is train and validation accuracy, and this is the train and validation loss. Okay. Here, from the observation, you can see this blue line is the train accuracy. It increases rapidly and reaches nearly 100% within the first 10 epochs. The first 10 epochs, you can see it has reached 100% accuracy. And the orange line is the validation accuracy. It starts low. At first, it started very low. You can see here at 50, or till it came and it maintained the same and it just dropped. So you can see till the 20 epochs, both the train and accuracy remained the constant. And then it continued the same. Means it is just interpreting that the model is learning quickly, which is good. Since the validation accuracy reached 100%, there is no underfitting. Means, however, the gap between the train and the validation accuracy is early epoch suggests the possible overfitting risk. And then here you can see the loss. The train, you can, as I told you, the blue is the training and the orange is the validation. It starts high, it's at the 6, then drops steeply into the first 10 epochs and stabilized. The validation loss is the orange line, follows a similar trend, but starts higher and decreases more slowly by the epoch 20. By the epoch 20, both losses stabilized at the low value. Means there is a quick decrease in both losses, validation and train losses. It shows that how effective the model is learning. Since the validation loss is close to the training loss, overfitting is not regularized. Means there could be improved the model generalization. And we can see here, as I told you, true positive and true negative and false positive and false negative. You can see I have for this confusion matrix. I had took 200 images of the cracks and 200 images. Sorry, 200 images of the overall the data set. 100 images is the cracks and the 100 images is the no cracks. Here you can see 95 of the images it has identified as the cracks, but 5 images are identified as the no cracks. Here you can see 99 images it is identified as the no cracks, but there is only one image it is identified as a crack. So this is the true positive and true negative and false positive and false negative. This is what I meant. Here for the performance metrics, you can see the accuracy, the model trained is 97%, the precision is the 98%, recall 95 means accuracy, precision, recall, and F1 score. These the performance metrics. Okay, so the model is correctly classified 97% of the images, and there is a 98.96 means it is a high precision. High precision means the model makes very few false crack detection. And for the recall, the 97% of the detects the model successfully detected of the actual cracks, but the 5%, here you can see, but the 5% of the cases it has missed. In case of the F1 score, it is the mean as a mathematics. It is the harmonic mean of the precision and recall balance the false positive and false negative. So we got the 96.94%. And finally, to say by any model we are using for the image classification and the object detection, we have to take the proper data set and we have to train the model properly. Unless we are not training the model properly, or we are not using the correct functions, there may be some errors. But the model gives the better results. It shows you got the 100% accuracy or 99% accuracy. But there is the some at the output, when you are taking the images output, there is some difficulties in the images. It only gives like the images with the no cracks or the crack images. It is completely depending upon the model training. The proper data set we use, how much data set we are using, what model we are using. I preferably suggest you to use YOLO, faster RCNN, and the wave mix model. These are the better models nowadays everyone are using for the object detection and image classification, particularly for in civil engineering side, for the concrete side, for the crack detection, or for the material optimization or the assessment. These are all the models. And for the proper using, we can we can use the automation in civil engineering as well, because everywhere the artificial intelligence and deep learning models are dominating. So to decrease the manual work and labor work, so we can use these automated models to get the better results and accuracy. Thank you.
Yes, sir. Ma'am, can we go for Q&A session? Chandrasekhar sir, may forward this to the Q&A session, sir?
You can ask the audience to pose any queries.
Yes.
We are ready. Myself and the host are ready
Okay, sir.
to answer
Yes.
their
Dear
questions.
participants, the Q&A session is open. Now you have any queries, you can ask either of the immediate resource persons. Sir, Chandrasekhar sir, we have a query on the chat box, sir. If you can see it. Excuse me, sir. Chandrasekhar sir.
She has given the presentation. Okay, if anybody having their doubts on image processing, I can answer. Wave mix theory, Hoshta will give the choice to Hoshta. Okay, right.
Yes.
Hoshta, come on.
Okay. Mhm. Yeah. How does the wave mix model improve interpretability compared to CNN and transformers in crack detection? Okay. So actually, in interpretability means wavelet. Here in the wave mix theory, we are using the wavelet transformers to which is a structured, and there is a multi-scale analysis when compared to the CNN. Wave mix model has the multi-scale analysis, and it is aware of the frequency mode. It is completely based on the frequency. So so yeah, it also, as I told you, it also reduces the complexity. Means how many times the model has to run and learn, like the epochs. So it is when compared to the CNN, yeah, the wave mix model is better. And in real world applications, crack data set are often imbalanced. What techniques can be used to evaluate models trained on such data set without biased results? Okay. In case of the imbalanced data set, as I told you, like augmix, and there are some Python tools as well. I will mention in the chat box. There are some tools like augmix, and there are some Python tools for this class imbalance. We can also create some synthetic data set. So this synthetic data set is nothing but it just for example, as I told you, if there is a crack image, um, it it takes that crack image. If there are less crack images, it will take the one crack image, and it studies how the image is there, and it creates a synthetic model of it. And in that case, the class imbalance is adjusted. And if the Vmix model outperforms CNN, but fails on another, but validation techniques would help diagnose the issues. Yeah, like CNN and Wavemix model, yeah, every model is designed for a particular type of we can say the CNN model is used and Wavemix model is used for the crack and object detection, image classification and object detection. Similarly, for the other type of models, yeah, there are some other. Yeah, but the third one I didn't really get. Okay, I will. I really didn't understand the third question. I'm sorry. What are the common challenges faced when using the neural networks? What are common challenges? The data set. The common challenges like the data set means if you have the proper data set, we can perform the crack detection very well. If the data set is not structured, or there is the improper data set, the model doesn't train well. The problem with the neural network is that neural network means it it deeply intensifies your issue. Like if you want to identify the crack, okay, if you want to classify the crack from the non-crack, okay, so it is completely depends upon the data set. Is the challenge the data, how you acquire the data, how you get the data, and how you train the model with that data. So it is the challenges we actually face with the neural network.
A small query from my side, ma'am, if I may ask.
Yeah, okay.
Question.
Do you recommend any?
For third question, host the.
Yeah.
Okay. Unmute and right. For third question, one of the audience is asked. So for that, data centric validation is one, and the second one is maybe model specific validation, and performance matrices and the robustness. So maybe a few more may be there, and for that I gone through that question, and I got these answers. The third one, if a VMix model outperformance CNN on a specific crack detection, for that, so data centric validation, one is the outperformance, and model specific validation is very much required to get a better performance of wave mix theory over CNN models.
Is it okay?
Yeah. Any more questions? Okay. What
Yes,
are
ma'am.
some of the problems that may be encountered when fitting a neural network model? There are some problems when fitting this neural network model, like maybe sometimes the model gets overfit and maybe sometimes it gets underfit. There are some, like I have told you, there are some parameters for in case of when we are doing the batch normalization, or we are when we are making the feature extraction. There are some, in case of if there is a hyperparameters are poor, in that case maybe some problems may encounter, and also if you have the insufficient training data, so maybe that's the case. And neural, okay, is there any limitations using for the structural crack detection? Okay, for a structural crack detection, yeah, there are some limitations. Maybe some limitations, like the data set should be like, okay, for the structural crack detection, the model itself doesn't know if it is a crack or not. So we have to train the model with the annotated images. As I told you, with the green bounding boxes in my presentation, we have to use that annotated images. So in that case, when we are using those annotated images, maybe there are some difficulties to obtain the crack appearances. So maybe it also differs between what type of materials we are using. So there are maybe the limitations in that case. Okay, more questions?
I hope that's it from the participant.
Okay.
That's a great session, ma'am. You have
Thank
taken us to the other level of engineering. You have introduced very new concepts actually. Some of us are doing on the
Thank you.
research work on that particular concepts, but you have made some topics very clear. Some we have to get trained to understand. Thank you so much for your patience, and thank you so much for your particular discussion. Thank you so much.
Thank you, sir. Thank you
And
for
coming to
your.
Chandrasekhar sir, thank you, sir. Thank you for great presentation. I would like to
Thank
hear
you.
some words.
Thank you, Ganesh Naidu and Naidu is there? Ganesh Naidu?
Yes, yes, sir.
Srikanth is also there? Yes.
No, sir.
Myself and my scholar, on behalf of my scholar, we are very much thankful to share our knowledge with us. If any further queries are there, you can share to your reason directly to my mail ID. They will give you the organizing ones, so that we will also find where we are lagging. It's a research. Research means continuous learning. Nobody is perfect unless otherwise you get a good product. So thank you, Ananda, for giving this opportunity. Can I leave with this?
Yes, sir. Thank you on behalf of Patients to Technology and Sciences and Civil Engineering Department. Thank you for joining us.
Okay, right. Thank you.
And Mrs. Hoshita, thank you for joining us. Ms. Hoshita.
I'm very happy for
Thank-
that Sivasai host the performance.
Right.
Okay, right.
Thank you, sir. Thank you so much.
Okay, right. Thank you.
Dear participants, the feedback link is given in the chat box. Kindly fill your feedback. And, thank you for your joining the session. And for coming to the tomorrow session updates, the tomorrow session will be starting by 2 p.m. tomorrow. So kindly join the session for the beginning. Thank you. Thank you, everyone. We'll wait for 5 to 10 minutes to fill the feedback. You can get the link on the WhatsApp group. Meanwhile, thank you, everyone.